Alright, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. What we're doing this time is Linear Algebra 1. We're in Chapter 2, which is Matrices. Section 2.3 is the Identity Matrix and Inverse Matrices. This lecture specifically, what we're doing is inverse matrix properties and the first method of finding the inverse of a matrix if it exists. What this method is going to do is we're going to be able to use a row reduction method or Gaussian elimination, Gaussian Jordan technically this time. This is the one method where I'm going to have to use reduced row echelon form. And if the reduced row echelon form of A, one of our matrices, is the identity matrix, the inverse existed, we can find it. If it's not, the inverse doesn't exist. What that's going to do is give us a method of always determining whether it exists, and if it does exist, it gives it to us. Then what we're going to do in the rest of the chapter is in section 2.4, we're going to switch to determinants, then determinant properties, and you're going to say, why are we doing this? This is horrible. That's going to give us another condition, systematically a necessary and sufficient condition for when an inverse exists, if and only if this thing determinant is not 0. And then we're going to get build an algebraic formula for computing this. Then what we're going to do in the chapter is we're going to use inverses. Remember, forest for the trees, we're not lumberjacks, we're architects. We're going to learn how to build these things systematically, which is an extremely long story. And then once we have those, we're going to use those to multiply matrix equations to solve linear systems. That's what we're going to do with this. And then we're not done the chapter yet. We'll do Cramer's rule. And then once we do Cramer's rule, then we'll move on to chapter 3. Let's get to it. All right, theorem, properties of inverses. If A and B are invertible matrices of the same size and they're square, the last result that we did last time was the fact that if you have an invertible matrix, the inverse is unique. There can only be one thing that multiplies. There can only be one inverse which does this in both directions. That seems magical at first, but in general this is actually true in any group or ring, whatever those are. You can watch some videos that we're going to do on this. But for our group or ring called the real numbers, if we know that 1 times A is A, we always say, and then we're looking for A times A inverse to be equal to 1. Should there be more than one that does that? Just take a number then. Should there be any other number than 1/2 that when I multiply it by 2 I get 1? No, inverse is unique for numbers also. There's only one reciprocal of a number, and we write this as 1 over A. And then that's the only one that'll do it. So that just means that it's true for matrices also. If you have the inverse of a matrix, we're going to get conditions for when that's true. But if you have one, there can only be one. It's like a Highlander. There can be only one. Now that we have that notion, further properties are, when I invert a matrix, it is invertible, and the inverse of the inverse is the matrix again. Again, if we're going to do that with numbers, I like to use this property first of all when we do this, but I have 2. 2 is invertible. Why? Because we know that 2 minus 1 is 1 over 2 exists. Long story short. And then, therefore, what if I want to talk about what his inverse is? What's the inverse of the inverse? 2 minus 1 is going to be 1 over 2, which is, using our algebra, going to be 2 again. So the inverse of the inverse here, using the algebra this way, instead of using just the fractional notation, the inverse of 2 is 2 again. So that's exactly the same for matrices. If we invert twice, we get the matrix back again. More importantly, this is extremely useful when we want to solve algebraically for a matrix in a system or something like this. So if you're going to invert twice, you get A back algebraically. For this one, if we want to invert the product, what that says is if A and B are invertible, their product is also an invertible matrix, and that inverse, which we know is unique, has to be B inverse A inverse, not A inverse B inverse. The other 2 properties, which are less relevant in this course because we won't use them as much, but we should list them for completeness, is you can interchange the transpose and inverse. Again, these all look like algebraic things, but this is not an exponent and this is not an exponent anymore. This says that this is a transpose where we're interchanging the roles of rows and columns, something that it's not an exponent. And then this says you're finding the multiplicative inverse of a matrix. Wait till you see in the next few sections and videos how we compute this thing. That is also not what you think we're computing. And what that's saying is if you transpose a matrix and then find that inverse, that will be the same thing as if you find the inverse of the matrix and then transpose that thing. You'll get the same outcome. The inverse of a transpose is the transpose of the inverse. And then our last one is the same thing. I didn't really define this, but for exponents, if we have a positive integer, a to the n is a multiplied by itself n times, just like for integers. And a to the 0 is the identity matrix. So if you have this a to the n inverse says that you can invert a first and then multiply it by itself n times. Property 4. Let's try an example of that. Actually, before we do an example, let's prove property 2, which says the inverse of a product is the product of the inverses in reverse order. What does that mean? Basically, before we start, and what are we actually doing here? A times B, we're saying, is invertible, but A times B, algebraically, you get shell shock because of the notation. This is, for simplicity, a matrix C. Again, when I have 2 times 3, I can call that 6, and then I can just work with 6 instead of 2 times 3, and you like that, but with the matrices, we have to leave them as the algebra. And Satan said, put the letters in the algebra, and then everybody's confused. So this is a matrix. The product is a matrix. Try to view it as just a single matrix is my point. We're saying it is invertible, we claim. So that means C minus 1 exists. And we now know is unique from the previous video. An inverse of any matrix is unique. So this product matrix, which is now a single matrix C, has an inverse. And that means that C, this product AB, C times its inverse is equal to the identity, and C inverse times C is also equal to that identity. Therefore, what we're now trying to show is that inverse matrix, which is AB is C, so that's what we're trying to say, and that's what the property says. We're trying to find out what that inverse is. And it tells us that it's not A inverse B inverse, but it's B inverse A inverse in that order specifically. So this is what we're trying to show, that the unique inverse of this product is this matrix. And it looks weird in the notation, and it's hard to figure out what the heck is going on. And the statement was just listed. Now what we're saying is, hopefully you can see it now, we're saying that the inverse of this product is a unique matrix, and it happens to be this matrix, B inverse A inverse. Now let's prove why that's true. We're going to show that B inverse A inverse times AB is the identity. I put the question marks because I haven't shown it yet. I claim that I'm going to. And all we're going to use is the previous properties of multiplication and then inverses, and we can get at and using the definition of inverses of A and B. All I'm doing now is assuming that, remember, A is invertible and B is invertible, so we know that these guys exist. So we're allowed to create this thing because we know A inverse exists and B inverse exists. So starting with that, if I have AB and then I multiply this by B inverse A inverse, that equals, first of all, what I can do is, this is B inverse, I can associate the brackets and write this as A inverse A. Bab. Now I have, as soon as I have this, I have the property and the fact that A inverse exists. I know that A inverse is the identity matrix. And I know that the identity matrix times any matrix is that matrix. So this now I can write as B inverse identity times B. It doesn't matter where you put the brackets. Associativity says I can put it either way. But now what that says technically is identity times B leaves B alone. So that will give me B inverse times B. And I know B is invertible, so B inverse times B is also the identity matrix. I already know this. So then I can use this, and this says this is the identity. And what that says by definition is B inverse A inverse is an inverse of AB. It's an inverse, but it has to be the inverse because they're unique. We see that B inverse A inverse is the unique inverse of B. Now let's do an example. Okay, what we're going to do is we're given 3 matrices, A, B, C, and we're going to squeeze in this example, I'm going to squeeze in one more property. Couldn't help myself. What we're going to do is show that AB equals AC, but B doesn't equal C. What that says in general is we don't have the cancellation property. We can't just cancel A and say, oh look, A equals B. We have this for real numbers. If A equals B and then A times C, can we always conclude that B equals C? It turns out, no, we actually have a condition. What is the condition? Luckily, in a larger structure, another structure we're not going to talk about in this class, I'll just mention it quickly, but we have also a ring structure for matrices and the real numbers, and that ring happens to also be a commutative ring, which has nothing to do with this, I couldn't help myself, but it also is a field, and what a field means is, why didn't you just say it that way, because I wanted to sneak in the Easter eggs. A field means that every non-zero element has an inverse, so if A is not 0, we know A minus 1 exists. And then we can conclude that we're technically multiplying both sides by the inverse and then making that equal 1, and then it would be 1 on that side, and you can conclude B equals C. We have to be even more careful with matrices. What that says is matrices are not a field, and nor are they an integral domain, which is another property that we're going to have, which is the zero product rule. If you have A times B, which is equivalent to this cancellation property, I won't get into it any more than I just did. If you have A times B is 0 in the real numbers, you can conclude immediately that A is 0 or B is 0. But now if you switch to the set of all matrices, let's take square ones so we can invert them, careful. Then now if I have A times B is 0, I cannot conclude that A is 0 or B is 0. The tunnel gets deeper because that you can't see why that's interesting, but if I'm factoring a polynomial and I have x minus A and x minus B equals 0 in the real numbers, that immediately says I have two roots possibly. That says x equals A or x equals B, because I know that this property is true. I have the cancellation property for real numbers. But if it's matrices now, if I do x minus A and x minus B is 0, we don't know if we have the cancellation property. We can't just cancel because we don't know if these guys have an inverse. If this has an inverse, I could multiply by the inverse, x minus A inverse on both sides, and then cancel and conclude that x equals B or something like this. But we have to be extremely careful. The algebra and stuff and the things that we start doing in the rules are not the same for matrices. It looks like a minus and an equals and stuff, and so we get exponents, so you start thinking they're the same thing, but they're not real numbers. The algebra and the properties are not exactly the same. Be careful. Now we're going to show that specifically, and then we'll show you how to get out of it in the general property. Tangent, pun intended. All right, let's do what it said now. I'm going to show that what's A times B. This is 2 by 2 by 2 by 2. The inside indices match, and it's well posed, and it'll be 2 by 2 also. This says I'm going to have 2, negative 1, negative 6, 3 times 1, 2, 1, 2. A mic check. 1, 2, 1, 2. And then we're going to have 2 minus 1 is 1. And then 4 minus 2 is 2. And then I have negative 6 plus 3 is negative 3. And negative 12 plus 6 is negative 6. Now what? I'm going to compute this. It said show that. All right, A times C is going to be 2 by 2, 2 by 2. They're well opposed. So I'm going to get 2, negative 1, negative 6, 3. Multiplied now by C, which is 2, 4, 3, 6, which is going to be a 2 by 2 matrix, which is going to give me 4 minus 3, which is 1, 8 minus 6, which is 2, 12 minus 9, which is negative 3, and negative 24 minus 18, which is negative 6. Oh, yes, they're equal. There's a vertical equals, whatever, it doesn't matter. They're equal. See? AC equals AB. But clearly, B, which equals 1, 2, 1, 2, does not equal 2, 4, 3, 6, which is equal to C. So what's happening here? You can't just cancel the A is what it's saying. Why is that? A, it turns out, doesn't have an inverse. If you look at this guy, the determinant is 6 minus 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 6. You don't know how to compute these things, but it's this minus minus this. So you're going to get 6 minus 6, which is 0. So I have a condition, and it tells me quickly once I know this that he has no inverse. So you're not allowed to just cancel it. And this also is the lazy way of writing this cancellation rule. They say, if you have this, then you can do this as long as A is not 0, but then you forget the condition A is not 0 all the time, and then you just think you can cancel all the time. What I need to restart training you to do is apply the multiplicative inverse to both sides. Don't cancel, apply the inverse and apply the algebraic rules that we have, and then you will systematically get the correct answer. Let's show you now if and when we can cancel. Now what we're going to do is algebraically, without even knowing, I don't even really need the matrices anymore. What I'm going to do is algebraically say, give conditions if and only if it's A. It's not B or C you need to worry about at all, first of all. Nor do I need to know what A looks like. I don't need to know what the components are. All I need to know is, it turns out eventually it will hopefully become Pavlovian. All I need to know that A's determinant is non-zero, therefore the inverse exists, and then that's the condition that's going to happen. Instead, let's phrase it as a theorem. Theorem, if we have that the product AB is equal to the product AC, and there's a second condition, A minus 1 exists, and you should be asking yourself, how do I determine whether it exists and how the heck am I going to find it? And that's what we're going to do in a second for 2 by 2, and then in the next video we'll do the general ones. Then what we're going to do is, then you can cancel. This implies B equals C. Proof. If I have AB equals AC and A minus 1 exists, I'm going to multiply both sides by the inverse. That says A inverse AB equals A inverse AC. On the left, it has to be on the left because if I flip these, I might not get the same thing. So I can't just put A inverse on this side. I don't know if I can do that. And you can't flip anything around in here. That's what our rules say. It's not commutative. But I can associate brackets. So this is now if and only if A inverse A is B, and here A inverse A is C. This is identity because he's the inverse. So that gives me IB equals IC. Identity leaves somebody alone. And that says B equals C. I don't even need if and only ifs, but QED. What it was to be shown quod erat demonstrandum. Therefore, we have this cancellation property, but it's not an integral domain, or we don't have this nice cancellation property like the real numbers. You can only cancel when the inverse exists, and just because it's not zero doesn't mean the inverse exists. This is a nice example of a 2 by 2 matrix, which is not the zero matrix, but it doesn't have an inverse. We can't just cancel by this matrix. Okay, a couple more results. They're essentially saying identically the same thing. These are also equivalent statements, but Mark Solomonovich likes to parse them out, and so do I. I concur, so I'm going to state them both separately. And then you can sort of erase this one. This is the more important one, but the proof of these is the idea of what this is going to be, and I'll explain it in a second. Let's do the theorems first. How do you get it all out at once? I wish I just had osmosis through the camera, but we don't. The first theorem says a square matrix of size n is invertible, which means that the inverse exists. This is an existence statement. If and only if the reduced row echelon form of that matrix is the identity matrix of the same size. And theorem 2 says a square matrix of size n is invertible, or the inverse exists, if and only if the rank of that matrix is n. Remember, the rank is the number of leading entries, or the number of non-zero rows in row echelon form. And that's going to be the same thing. If you get the identity matrix, you'll have n leading ones on the diagonals and zeros everywhere else, and therefore the rank will be n. So if you're invertible, then the identity matrix is your RREF, and then that means that your rank will be n, and you can prove vice versa. Instead, what I want to do is also in the proof of this, we get a systematic method of now constructing the inverse or stating whether it doesn't exist. Again, this is the law of excluded middles. In that scenario, my point being is either an inverse exists or it doesn't exist. And so we need a method to say yes or no to that law of excluded middles. And ideally, if it's a yes, we want a construction method to have it. We don't need to construct it here because it doesn't exist. What we're going to cleverly do now in this notation is, and in the idea of the proof of this, what we do is if we write down now the identity matrix, and now instead of an equals, it's not an augmented matrix, it's a block matrix. It's a concatenation of two matrices. We're sticking them together. And then what we're going to do is we're going to take the n by n matrix A and write it in the front block. And then we're going to write down the identity matrix of size n behind it. Then we're going to use row operations. Row reduction goes here. And then we're going to use our theorems essentially. If the reduced row echelon form of that matrix A, if I can turn A into the identity matrix in reduced row echelon form, This might even be REF or less. As soon as I get a row of zeros, I can stop. The jig is up. When I do this process, if I can turn A into the identity in the reduced row echelon form, in that second block, the inverse will magically appear. We can use elementary matrices to prove and show why this is also true in a different method, but we won't get into it. All you need is the method. And if you, along the way, try to turn A into an identity matrix, if you get a row of zeros, that means in row reduction, when you go all the way to RREF, you could never get the identity matrix because you have a row of zeros. An identity has to have ones all the way down. So as soon as you get a row of zeros, that says you could never create the identity matrix, which now tells you logically by this theorem that if you can't ever create the identity in reduced row echelon form, the inverse doesn't exist. And that's what we're using here. So we now have a systematic method of showing either constructing the inverse or showing that it doesn't exist. Let's try that with 2x2 matrices, but you're going to see why we want the other method eventually. Row reduction, fractions abound, and reducing all the way to reduced row echelon form in a 5x5 matrix, if I give it to you, is less fun than you may have imagined already on your own. Let's try that for a 2x2. Okay, we're going to, and this is where we make you decide, and this is what you hopefully should have been asking yourself already, but if you didn't, now the good questions after we do theory will ask you exactly that. When does the inverse exist, and how do I tell, and what does it look like? How do I get it? So we're going to use that method systematically of writing a block identity and then using row reduction to reduce row echelon form. This is the only time in the course that I will explicitly require that you do reduced row echelon form all the way, because we need to see whether we get the identity matrix once we do that. What we're going to do is write a block I2. And so there also, what does that mean? That means I just write A, 3, 7, 2, 5, and then I write down the 2x2 identity matrix. That's the 2x2 identity matrix. Once I have that, now I just carry around the row operations to all the rows, the whole thing, and I just treat this as one row and another row. Then what I'm going to do is I want to get a leading one in the top left corner, eliminate below, and turn this all the way into reduced row echelon form. I do not want fractions. I have a larger structure of the theory inside my brain, so I see immediately. I have another check which we're going to do in the next couple of videos. It's called determinants, and then a condition, and necessary and sufficient condition for when a matrix is invertible. That's if and only if its determinant is not 0. And here it's 15 minus 14, which is 1. So what that tells me is not only is it non-zero and it is invertible, but the determinant is 1, which is in our formula is 1 over determinant, and it's a 1, so there's not going to be any fractions is my point. There will be no fractions in the inverse of this matrix, but if you row reduce and just divide by 3 and divide by 2, oh, you're going to have all kinds of fractions to when you finally get to the end, you're going to realize that you had integer solutions, and that is going to be extremely frustrating. My point being is, work smart, not hard. Don't divide by 3. What's 3 minus 2? Oh my, yeah, a 1. So I'm going to do row 1 minus row 2 to get a leading 1. Therefore, row 1 goes to row 1 minus row 2. That will give me 3 minus 2 is 1. 7 minus 5 is 2. 1 minus 0 is 1. And 0 minus 1 is minus 1. That was a whole lot better. And then we can keep this 2, 5, 0, 1. Enter noodles. There was growling. That was noodles growling at the baby cats. I know. They're not big yet. They can't roll with the main cat, can they? No. All right, now what? Once I have a leading 1, okay, you go do that. I'll do row reduction, reduce row echelon form. I have a leading 1, I need to get rid of this guy. That tells me that I'm going to do row 2 goes to row 2 minus 2, row 1. That will give me, I know, 1, 2, 1 minus 1. Now we're multiplying by negative 2. 2 minus 2 is 0, that's why I did it. 5 minus 4 is 1. And then 0 minus 2 is negative 2, and 1 plus 2 is 3. Meow, meow. He howls like a dog. You're a cat, not a dog, and we're shooting videos. Be quiet. He's running around now. Now what do I want to do? This is REF. Can I stop? No, this is the only one where I can't stop. Won't stop until I get rid of that 2. That 2 has to go away. So what am I going to do now? I'm going to do row 1 is going to finally get changed. And row 1 is going to go to row 1 minus 2, row 2. That's going to give me, this won't change. Coincidentally, I know this is the bottom row of my inverse matrix because this is the bottom row of the identity matrix. So once he's there, once I've turned A into that bottom row, that has to be the bottom row of my inverse. And then now what am I going to get here? we're going to multiply by 2, so I'm going to get 2 minus 2 is 0. 1 minus 4, or minus 4 is 5, and negative 1 minus 6 is negative 7. That is, now we've turned that into I2 times the inverse matrix is what we say. In particular, what does that mean? The inverse of this matrix is 5, negative 7, negative 2, 3. Do you think we did it right? Do you believe me just because I said it and we're in the video? Because I probably checked in the editing, so I got it right. There's a way of checking. Let's do that for a second. What I'm going to do is, now that you saw that, I'm going to sneak it in. As soon as you think you have the inverse and you've done all that work, you can see this is 2 by 2. Try this for a 5 by 5, and you'll see, oh, this was not so fun. It's like I would like a formula or something. Yeah, just wait. We'll get the determinant and then the formula. We'll get a better method. But for now, we've got one. Technically, what this gives us is for any size matrix, you have a way of computing the inverse. It's less than fun, I'm going to imagine, from your point of view. I still kind of like it. But after we do all that work, can you check? What's the definition? A times A inverse better be the identity matrix. So check and see if it works. A was the first 4 prime numbers. And then his inverse is, you flip the diagonals and put negatives on the off diagonals of 1 over determinant, which was 1. So there's a formula. And so what I'm going to get is, this should be 5, negative 7, negative 2, 3. And what do I get? 2 by 2, 2 by 2, well posed. I can do the multiplication and I'll get a 2 by 2 matrix. And what am I going to get? 15 minus 14 is 1. Negative 21 plus 21 is 0. 10 minus 10 is 0. Negative 14 plus 15 is 1. Oh, A times A inverse is identity. You have a way to check whether you did that computation correctly. I know by the time you're done, you're exhausted, but at the end, when we do lumberjack and cleaning, you have to clean the tools and wrap up everything and then clean up. The most important part of doing a job is the cleanup. The cleanup here is checking that you got it right. Not every question has a cleanup, and then you're like, I don't know, I have to just leave it. This one does. Let's do one more example because I want to show how to compute an explicit formula for inverse for 2 by 2s. But of course, before we do that, read the question again is good advice, and make sure you've answered what they wanted. I did number 1. Yes, the inverse exists, and the inverse is 1 over the determinant, which is 1. I can regurgitate it now, which will be, I flip these and put a negative on those guys. Therefore, for this guy, what am I going to get? This one, we're going to have A block I2 is going to look like 6, 3, 4, 2, 1, 0, 0, 1. Again, what am I going to try and do? Oh, now the jig is up, actually. The GCD of 4 and 6 is 2, which is not 1, so I can't actually create a 1 from combinations of trying to add and multiply these guys together. So this time, I do have no choice, but I have to divide by 6 or 4 to get a leading 1. I'm going to just divide by 6, and you'll see that it won't matter too much. We won't have to do too much computation, but this is still not the most ideal method. What we're going to do from there is, I am going to do row 1 goes to 1 over 6, row 1. That's going to give us 1, 1 half, 1 sixth, 0, 4, 2, 0, 1. Then we want to multiply by negative 4 to get rid of this. So row 2 goes to row 2 minus 4, row 1. We could have also multiplied by negative 6 in this row and negative 4 in this row and then added to get a 0. You can do it this way. Shear some sheep. I don't care which way you do it. This is the way I'm doing it. Therefore, now once I do that, 4 minus 4 is 0. That's why we did it. Then negative 4 times 1 half is negative 2 plus 2 is 0. Oh, and then what are we going to get here? We're going to get, it doesn't matter. It doesn't matter. If you know what we're doing, I could have computed, but we're going to get 0 minus 4 over 6, which is negative 2 over 3. If you want me to simplify specifically. And then here, this one was nice. I'm going to get 0 and then a 1. But why did it not matter? As soon as I get a 0 on the left-hand side, I know that 0 is not this. I can't ever get the identity matrix, the 2 by 2 identity matrix from this scenario now because I have a row of zeros here. So what that immediately says is A minus 1 does not exist. Now let's do one more problem. Yeah, is that how everybody else is? Next, we're going to do the Charlie Brown. No. All right, final one. I don't care how many we've done. I want to do 6 more, but they said keep your videos to roughly 10 minutes because the attention span of the average person doesn't give a crap about mathematics. Find the necessary and sufficient conditions for when a 2 by 2 matrix has an inverse. This is the goal of what mathematicians want. We want an if and only if condition for when I can tell whether the inverse exists, and then I want an explicit formula for that. Baby steps. We're going to start with the 2 by 2 matrix, and then you're going to realize the power of having this meme of, this is how you compute an inverse. It's a formula, and thank you for that meme. For the 2 by 2 case, what are we going to do? I extremely like this problem, but just the way that we phrase and flesh out. I'm going to use linear algebra to solve another linear algebra problem. I'm going to use systems of linear equations to find conditions for when this is true, using the definition of what an inverse means. And cleverly, I've already given, so in case you didn't know, it seems like there's 4 unknowns there because we don't know what the inverse looks like, and it seems like I'm going to look for in some kind of system of linear equations for those 4 unknowns, and then we're going to find the conditions on A, B, C, D, which is actually AD minus BC is not 0, will be the necessary and sufficient conditions for it to exist, and then we can, why is that? Because we have to divide by that number, and you can't divide by 0, and so we're going to get a condition, and then we'll get an explicit formula for that inverse. I'm not going to do it. I'm going to leave it to you to flesh out a couple of the steps because I'm going to say wave a hand at do that last part, which is the hardest part, and that's why I leave it out of the video. Starting off, what I'm doing is phrasing this as, by definition, if A is invertible, we're going to assume, or we don't know. But if that's going to be true, we're going to have A inverse is the identity 2 by 2 matrix. Phrasing that with what we have, actually, we know what I2 looks like also. That's going to mean we're going to have A, B, C, D. We need this. We need A, B, C, D times our 4 unknowns, x1, x2, x3, x4, to equal the identity matrix, which is 1, 0, 0, 1. And then now this is exciting because now if you look at a couple of videos previous, we define in the first video on what a matrix is, we say when we have equality, and you're like, when would I ever use that? Here, when is this matrix equal to this matrix? Remember, this is a third matrix, which we're going to compute in a second, but he's a product, but he's still a 2 by 2 matrix. First coordinate of this one will have to equal the first coordinate of this, and so on. But we haven't done this multiplication. So now we get to practice multiplication first. It's got so many things all in one. The definition of inverse, matrix multiplication, the equality of matrices, and then you're going to see how solving linear systems from this scenario. What do I get? This, it's non-homogeneous because of the 1. Matrix multiplication says, on the left-hand side, I'm going to get a 2 by 2 matrix. What am I going to get? AX1 plus BX3. AX2 plus BX4, and then I'm going to get CX1 plus DX3 and CX2 plus DX4. I've done that before. That's the left-hand side, and that equals our identity matrix. When are these 2 matrices equal? If and only if this entry equals this entry, and I'm going to get AX1 plus BX3 equals 1. This entry has to equal 0. And then I'm going to get 0, and then I'm going to get 1. Oh, palindrome, which is a prime, I believe. Anyways, that's nothing to do with what we're doing. Here, I'm going to get AX2 plus BX4 is equal to 0. Here, I'm going to get CX1 plus DX3 equals 0. And here, I'm going to get CX2 plus DX4 equals 1. And then what are we going to do? Erase the board because I need a bigger space. From this now I can see I have a linear system. There's how I cleverly did that. I'm going to erase that now. From that scenario, oh, that seems so complicated. And if you look in a previous video, we have this game that we play, find all A and B such that the system has one solution, no solution, infinitely many. Well, what we're doing there now is, it wasn't a tail-chasing exercise to find all of those coefficients. Now exactly what we're doing is find the A, B, C, D such that we have a unique solution in this system so that it's invertible. Long story short, ... we get an augmented matrix. A, 0, B, 0, 1, 0, A, 0, B, 0, C, 0, D, 0, 0, and 0C, 0D, 1. Then what we want to do is reduce row echelon form all the way to this, and what we end up getting is that, remember, this was, we're finding x1, x2, x3, x4, and it turns out we're going to find that x1, x2, x3, x4, if AD minus BC is not 0, we can divide by that and we'll get a unique solution. So now I'm waving a hand that you have to do all these steps and row reduce this. I'm not going to get into it in here, but that's what you're going to do. Again, be careful, there's conditions. You can't just divide by A. You get two conditions. If A is not 0, you can get a leading 1 and then start manipulating. Otherwise, be careful. Row reduce that. When you do that, you get a unique solution. And what are these now? Oh, now I'm going to have to be clever. Remember, this was x1, x2, x3, x4 was my original matrix for the inverse. And what this is going to be is, this one is going to be d over AD minus BC. x2 is going to be negative b over AD minus BC. x3 is going to be negative c over AD minus BC. Yeah, nobody said it was going to look nice. And then x4 is going to be a over AD minus BC. You will find out later that this is this is the determinant. That's 1 over the determinant, and these are the cofactors C11, C12, C21, and C22. We'll get to that in the next couple of videos. Right now, what that says is we have an explicit formula, long story short, for the inverse. Let me clean that up for you for a minute and then explain even more in this problem. We also have scalar multiplication of a number times a matrix. So let me write that up, and what's the formula? So yes, the necessary and sufficient conditions are, we have an inverse of a matrix if and only if AD minus BC is not 0. And in that case, we have an explicit formula for the inverse. This is what you put those into here, and we have a nice formula. Let's write that down. All right, to finish off and recap what we're saying here, we now found necessary and sufficient conditions. I waved a hand in a couple of the steps, but we found necessary and sufficient conditions for when a 2 by 2 matrix has an inverse. This number AD minus BC, A times D minus B times C. So it's going to be the main diagonal minus the off diagonal as a 2 by 2 determinant. That's going to be extremely useful in the next section. If that number is not 0, which is in fact the determinant of A. If the determinant is non-zero, then the inverse formula is 1 over the determinant cofactor transposed, or the adjoint. What? For now it's just a formula, but you're going to see we're going to generate a formula for this, and we're going to switch from 2 by 2 to n by n eventually, and we want to have a nicer formula. So when we do that, it will look exactly like this. And coincidentally, you're like, that doesn't quite look exactly like what we just did with the x1, x2, x3, x4. Well, this is a number. Scalar multiplied by a 2 by 2 matrix. How do you do scalar multiplication? If this is k, k goes onto every coordinate. So I can write this as d over AD minus BC, negative b over AD minus BC, negative c over AD minus BC, and a over AD minus BC, x1, x2, x3, x4. That's the inverse of a matrix. And remember, this is a number. This is a matrix. Scalar multiplication goes into each coordinate. And the difference here is, once you can see the formula now, when I have a 2 by 2 formula, first of all, it's much quicker to compute than using row reduction. But row reduction may get horrible fractions, and then you have to row reduce all the way to reduce row echelon form in a big matrix possibly. But here, regardless of the size of the matrix, if the entries of your matrix are all integers, then these cofactors we build will also be integers, you can notice. And then the fractions come at the end when we multiply by the determinant. So we can construct the inverse even if it has horrible fractions in its entries. The fractions will come at the end once I multiply by 1 over the determinant. So it's a much better way computationally of computing this eventually. You'll probably disagree for the first couple sections when I show you how to compute determinants. But once we get good at it, cutting down other kinds of lumber trees, we're going to go to a different country and cut down different, where the redwood, those are much more dangerous now, but we're still going to do it. And when we do, we will systematically construct a formula for all n by n matrices and have an inverse formula. Let's do one quick example of using the formula with the same matrix. All right, if we have a matrix, remember this is AD minus BC. So first of all, we need AD minus BC is 3 times 5 minus 2 times 7, which is 15 minus 14, which is 1, which I was calculating in my head before. That's how I knew that it was invertible. That tells me immediately, which is not 0. That says a minus 1 exists, and we have explicitly a formula for that. What is that? It says that the inverse is going to be 1 over the determinant, 1 over 1, which is nice in this case, times, now what are we going to do? We're going to flip these ones, 5, 3, and we're going to add negatives to those ones, negative 7, negative 2, which is 5, negative 7, negative 2, 3, which is exactly what we got using the other method. Therefore, we have the inverse of this matrix is we flip the entries. For the algebraic formula, you do 1 over the determinant here. I hope it kind of wasn't a 1 because you'd see that we'd have to factor it in. But because we got 1, what you do is you flip these ones and put negatives on the off diagonal. Don't do it that way. What we're going to do in the next couple of sections is systematically derive the formula for what we call a determinant, which is going to be a machine to help us create the algebraic formula for the inverse of a matrix of any size. Then we have a systematic way of building the inverse of that, and by the time we do that, don't forget what we want to use these inverses for. We want to create these things so that we can multiply both sides of a linear system by the inverse of a matrix and solve for the unknown solution vector x1 to xn. Please subscribe right here, hit the notification bell. I'll see you next time.